for dynamic allocation. My emphasis for this talk is going to be primarily on access and allocation of memory as it relates to performance. We've had a lot of other good talks, like we had one earlier today, kind of explaining general uses, past sync arguments by value and all that. So I'm not going to spend too much time on that. I'm just going to have a brief overview at the beginning and then dive into the performance aspects of it. Okay. So first the basics. There's two ways you can allocate memory in general. Kind of automatic storage, allocating from the stack, looks like that. Just declare a type name and then the variable. Or from the free store, or the heap. There's also global and static allocation, but I'm not going to be talking about those here. And the three general ways that you would allocate memory from the heap look something like this. You say new, T, standard make unique, or standard make shared. And a lot of times you see advice kind of like this, kind of your hierarchy of ownership. First, you should prefer automatic variables. And then if you can't use those, then unique pointer. And then if you can't use that, then shared pointer. And overall, I do agree with this advice. But I find that a lot of times when people give this advice, they just kind of give you this list, say, do it. And then they don't really explain, as much as I would like anyway, why they're in the order they are. So if you note one important thing, raw pointers are not on this list. Typical code, you shouldn't say new T, it's stored in a raw pointer. And so in my talk, I'm going to be talking a little bit about, I might mention a large value or a small value. So for purposes of this presentation, a large value is returned by size of, so the stack allocated space. So for example, a vector of T is small. On most 64-bit systems, it's going to be 24 bytes. It's going to have a pointer to the beginning, a size, and a capacity. And that's regardless of the number of elements. In comparison, an array of 1,000 characters is large. It's 1,000 bytes. So the important thing is that small values are cheap to move and large values are expensive to move in general. So for instance, vector, just 3 pointer assignments essentially, whereas array is going to have 1,000 character assignments. So the ultimate question here is, why would we use dynamic memory? So kind of obvious one everyone thinks of, runtime sized collections. Vector, dec, map, set, all of these internally are using dynamic allocation. And I'll get into the performance of that a little bit later. I just wanted to briefly mention that because a lot of people, that's the first one they go to. They want to see that up there first. Instead, I'm going to go to polymorphism. So dynamic allocation is required for runtime polymorphism in function returns. So if you want to return a pointer to a base, in general, you should do that with a unique pointer. It's also usually required for member and local variables. So if you want to store a pointer to a base, store generally unique pointer to the base. And it is not required for function parameters. A lot of people, when they're kind of trying to figure out, I want to have my polymorphic base class, they think that that means that they have to dynamically allocate. So you can have a function that accepts a reference or a pointer to the base class and pass in the reference or pointer to the derived, and it'll automatically convert down. So if all you're doing is using this object for runtime polymorphism, you don't need dynamic allocation for that. It's only if you're returning it from a function, so when you create it, or when you're storing it in some class at a later point, that the dynamic allocation will always. Yes?
I'm not sure I understand. If I created a derived class on the program stacks, why would I want to somehow convert it to a base class?
Okay, so the question was, if I create a dynamic object, or rather a derived object on the stack at some point in my program, why would I want to convert it to a pointer to the base class? Mm-hmm. And so the reason for that would be if you have a function that accepts the pointer reference to the base class, you have that one function compiled into your code. You may always know in a particular part of your program that you're going to use this particular derived. And in that case, you don't have to dynamically allocate the derived class. Maybe in general, you don't know, you're using some factory function. But just for this part here, I know this is always going to be a lion, but I still want to use it with this function that operates on animals.
Let me give you a concrete case. Suppose
Okay.
I have a particular allocator, and I'm going to create a vector with that particular allocator or whatever.
Uh-huh.
So I would create, now I'm thinking of, I realize we have the scoped allocator model. When we get to polymorphic allocators, I would create a buffered sequential allocator, and then I would pass this, it'll be called a memory resource or something, it's a different name, but basically what it is it's a derived class from a base class. And I can just pass that in directly. I don't need to do anything other than take its address. So I'm passing in the address of the derived class, and it'll go into the function automatically as the base class. It'll do the standard conversion. So I guess what I'm asking is, within the scope of a function, why would I want to do this? I'm just looking for an application. I mean, I don't see one. Do you see what I'm saying?
I think what he described is exactly what you said.
Yeah, so the question was basically you can rely on standard conversions to pass things through there.
Yes.
Why do you have to do anything special? And I agree with you, so maybe I'm not explaining it very well. That, yeah, you do rely on the standard conversions. It's just that you don't necessarily have to say new or make unique or make shared or anything to get that behavior.
Right. Okay. Okay. Maybe.
That's all I was trying
Okay,
to get at there.
Describing the same thing two different ways.
Yeah, so because some people, when they hear runtime polymorphism, they associate that always with dynamic allocation. And usually you have that, but you don't necessarily need it.
Okay.
That was the only point I was trying to make there.
Well, I agree with that.
So those first two cases that I covered are kind of, the two obvious cases that you learn about, introduction to C++, how to dynamically allocate memory. So there was an article, I believe it was Scott Myers who wrote or spoke about, think about move as an optimization of copy. And in most cases that is true, but sometimes you can use dynamic allocation to achieve moves that are not just an optimization of copy. So the reason for that is because some objects have to remain at the same address. It's also referred to as reference stability. An example of this would be standard mutex. Standard mutex is not movable, but you can have a unique pointer to a mutex. You can move that handle around and still have the mutex operate and lock things. Another example would be anything that other objects reference. So, I could create a function in here, I can pass out pointers and references to it, and then I want to transfer the ownership to someone else. As long as they're storing references and pointers to the object and not the pointer to the object, I can move that pointer to the object around all I want. So move the unique pointer that owns the object without invalidating anybody's pointers or references. Another example, in multi-threaded code, you could have a class that encapsulates a thread. And maybe you want to store this class in a vector. If you just put the class in the vector directly, then you could add, say you add the second one and that forces a reallocation. Now your class is moved, but internally it's encapsulating a thread. The thread could be running. You move the class, this pointer becomes invalid. So instead you could store unique pointers to the class in the vector. No amount of adding to the vector, sorting the vector, moving things around is going to change the location of the class that you actually care about. So it's kind of an extra layer of indirection to keep your references stable. These are all fundamentally addressing the same problem, that you can have many things trying to reference this and you need to make sure it's always at the same location in memory. So yeah, the point is that unique pointer to T is always movable, even if T is not movable or not safely movable. Another situation is when an object could be expensive to move, but you still want to return it from a function or transfer ownership to it. So the important thing here is that a unique pointer to an object is always going to be fast to move. It's always going to be 2-pointer assignments. Whereas your other objects, it could be an array of 10,000 integers, or it could be a class with a whole lot of fields in it. If you want to transfer ownership around, or say you have it in a vector and you're needing to sort it, it can be very slow to move this object just because the size of it is pretty large. Whereas with unique pointer, it's always going to be the same time.
If you go back to, and I can't remember whose presentation it was yesterday, because there's been so many, but in those cases, those types of objects aren't even really movable. They're really only copyable, even though they implement move operations. Everything has to be copied anyway.
Yeah, so the point was that for those objects, they aren't really movable because copy is the same thing as move. But you actually can have some kind of counterexamples to that. Like you could have a class with, say, 150 bytes of ints and whatever inside of it, and it also has a vector. So move is better than copy, but it's still pretty expensive.
I was just
Yes.
going to suggest that if this was a standard array of string and you move the array, you don't have to reallocate the memory for the strings.
Yeah, so the point was that if this were a standard array of, say, standard string, you would not have to reallocate the memory. Although in the case of array, if you move the array, it'll move each of the contained objects. So you would not have an allocation in that case either, regardless of how you store
Yeah,
that.
you would have to move all of the strings over, but you wouldn't. The strings themselves wouldn't be.
Yeah, okay, yes. Yeah, so I kind of mentioned that. Another kind of issue here is that you don't have to worry about running out of stack space with unique pointer. It's only 8 bytes, whereas if you try to just create an array of 1024 integers nested twice, that's 4 megabytes. That'll probably overflow your stack. I know some compilers are coming out with, infinitely sized stacks, so to speak, but a lot of compilers do not have that. So I want to get into a little bit of the performance of containers with regards to how they allocate memory. So first I'm going to look at the sequence containers, dec, list, vector, and also a vector of unique pointers. Sometimes it could be called like a moving vector because it moves the elements in there. I'm going to be referring to it in my slides here just to save on space. So the source of this data, you can find the code for the tests that generated the graphs that I'm going to show you here at that URL. The tests were run compiling with GCC 482 with these flags, and it was run on an Intel i5 machine. So first, I guess I should explain what the test was. Some of you may have seen a presentation by Bjarne Stroustrup where he compared the performance of vector and list. And the test that he ran was he generated a whole bunch of integers and inserted them into the container in order. So that involved doing a linear search and insertion. So in the case of list, linear search, constant time insert in the middle. In the case of vector, linear search, insert in the middle, and then shift all the elements over. So I repeated that same test, but I varied the object sizes, and I also added in dec and the vector of unique pointer. So on this graph, you can see that with 1 byte elements, list performed very poorly for this test. Even as we go up into the hundreds of thousands of elements, the growth rate is very bad for list. Moving vector not doing very well. Dec and vector pretty much the same. And the reason for this is because when you have such small elements, the time it takes to iterate over the list dominates the time it takes to insert and shift elements over. So because dec and vector have kind of greater locality of reference, that helps out here. But as we increase the size of the elements, the difference decreases until at about 60 bytes, the vector of unique pointers becomes the highest performing solution. That is to say, the size of the elements that we are, like the T in this sense. And actually even up to 100 bytes, vector and dec are performing better than list at this task. It's not until we get to 200 bytes, that list beats it out. But even as we increase the size of the elements, list never overtakes moving vector. And this is the same data just presented in a different graph. This was with 1 million elements in the container. We perform the same operation. We see that the vector of unique pointers, the moving vector, is pretty flat. and the list is also pretty flat. So at very small values, like we saw, vector and deck are better, but they get worse performance. But I think the interesting thing to note here is that the slope of list and moving vector are about the same. And that's really just the cost of allocating slightly more memory, because both of these are independent of the size of the contained value. Because this is all it's doing is moving unique pointers, all this is doing is relinking nodes. So you wouldn't expect at any size for list to ever overtake moving vector.
On an
Yes.
earlier slide, it seemed that DQ, and by the way, is the legend right here, or is that?
No, that I guess got messed up.
Okay, could you go back just?
Yes.
Just, I want to ask specifically about the, little further, if you could, but, like when it was small. What I want to know is that why is the vector worse than the DQ when the linear was supposed to be, the linear search was supposed to be the dominant part?
Okay, so the question here was why is it that the green line, the vector, is not performing the best for the smallest elements? Is that?
That's it.
Okay. So let me jump ahead. Actually, I have a little bit of explanation of results, and I'll talk about that in there. Yeah. So in general, the explanation for the results, as I said, is locality of reference, which explains the plane vector's performance for small elements. But too far. I guess I didn't have that in my slide. Okay, so the reason that the deck always performed better than the vector for this test, I believe relates to just the way that deck allocates in blocks, in small blocks. So the shift operations were slightly cheaper. I think the search time for both was going to be very similar because most of your time is spent within one contiguous block of memory, and then occasionally you fetch a new block of memory. Because you're able to fit so many elements into a block, that separation of blocks did not make that much of a difference, but it does simplify the shifting a little bit.
Right. Okay.
So yeah, this explains yes.
Another possible factor is that deck never reallocates.
Oh yeah, that I guess would be the other obvious answer as you insert into.
Big of a factor in vector's performance?
Yeah. The other obvious answer that I probably should have realized here was that as you insert into a vector, occasionally you do have to reallocate the entire vector. One thing though that I think is interesting is that for most of the graph, we actually don't see, like this is the only graph where you really see any big spikes, and those you see those in list and moving vector. With vector, you don't see like at a particular size or number of elements a big jump and then mostly flat. It is a fairly smooth curve.
And vector does win in some of them, like this one.
In this one, further to the
Oh, right, yes.
yeah, because this is the amount of time for a particular number of elements.
Shallower slope is the winner.
Yeah.
Yeah.
So the locality of reference explanation explains vector's performance and deck's performance for small element sizes, but it does not explain why the vector of unique pointers, the moving vector, outperformed standard list on all of the tests. And so for that, you have to look into pipelining. So with a moving vector, you have your first element, and it points to some data. Your next element, it points to some data. So all of your sort of control information, all your pointers are all together. Whereas with a list, your data is here, points to the next data. It has to follow the pointers to figure out where to go next. So in this scenario, the moving vector, the processor can issue an instruction to fetch this memory. And while it's waiting on that, it can queue this next operation to fetch this next set of memory. So it can sort of hide the latency of the memory by enqueuing multiple memory operations in advance. Whereas with the list, it has to wait until the results of this fetch before it even knows where to go next. So you can't use, basically all of the processor's pipelining is useless. You have pipeline stalls on every operation with the list, whereas you don't necessarily with the moving vector. And so that brings me to a guideline about standard list. If you are iterating over it, you shouldn't use standard list because the cost of iteration is so high. There are very few situations where lists guarantees are actually beneficial. The one thing it does have that the other containers don't is iterator stability. So with vector, if you insert into the middle, all iterators after that point are invalidated. If you insert and it causes a reallocation, all iterators are invalidated. And iterators and references, I should say. DEC has similar vector invalidation rules, but references remain valid. Moving vector gives you reference stability in all cases, but iterators are invalidated. So standard list is the only sequence container other than forward list that give you iterator stability guarantees. Yes?
Boost container has what's called stable vector, which is
Yes.
effectively a vector of unique pointers.
So the point was that boost container has stable vector, which is essentially a vector of unique pointers. One issue, though, is that the boost stable vector, the iterators and the elements, I guess I should say, are somewhat larger because the iterator contains a pointer back to the container, whereas in the test that I ran here, the container is just unique pointers to the object. The object doesn't know about what container it's back in. So actually, I don't know how boost container handles move semantics with the stable vector.
Yeah, I don't know.
Yeah, that seems like that would cause an issue because it's pointing back to the container and the container might move. So that's another issue that just a vector of unique pointer. What's that?
I didn't know that.
Yeah, that is how it achieves stability. It's a pointer to the container and an index rather than a pointer to the actual element. Yes?
Yeah, I just wonder for a list of very small elements,
Mhm.
if you might still be better iterating over the list, because in that case, the next pointer and the data would be in the same place, so you're going to fetch a line into the cache, and you'll get both of them. And you go to the next, whereas with the unique pointer, you fetch the pointer, but then you got to go get another line in the cache for the actual data.
Okay, so the point was that maybe for small elements, standard list might have an advantage because essentially you're saying the allocator could allocate multiple elements next to each other?
Yeah.
Yeah.
You got lucky.
Yes. So in my tests anyway, that did not happen for the small set of elements. They weren't, rather, they were not given any sort of performance advantage. I did not look into the details of the allocator to see if it's allocating multiple elements in the same block. I do believe, however, that would still interfere with the same pipelining issue because it could fetch the block of memory and have it in cache, but it wouldn't necessarily know ahead of time that this is where the next data is. It still has to follow the pointer. That would be my explanation for why, even for small elements, we see that worse performance. And my other point with standard list is that if you're not iterating, then you don't need a standard list either. So I would actually recommend, I cannot come up with a single situation where standard list is the best data structure. The only few that I've thought of, for instance, in the implementation of a least recently used cache, you're probably better off with a standard forward list because you don't have the overhead of an extra pointer to back. Yes?
So I was a little bit surprised by the graphs that you showed. Usually when you deal with any of these, like an insert, how much does it cost, it usually looks like this, right? It somewhat flat, a little bit increases, then it jumps when you go beyond the level cache. Then it's a little bit more flat, and then jumps again when you go beyond level 2 or level 3 cache. I'm not sure it might have been in the beginning
Okay, so the point was that the graphs were surprising because he was expecting to see more of a jump when the size exceeds the L2 cache and then the L3 cache. I believe that the reason that you do not see this in the case of vector and dec is because you go through it, and then once you get through the size of the L2 cache, you bring in another set that can essentially fill up however much data you want and evict the whole old data before because you don't need it anymore. So that L2 cache eviction and fetching from L3 is kind of amortized over the cost of the entire collection. Yes?
Which random number generator do you use?
The question was, which random number generator did I use? I used the C++11 standard MT19937, the Mersenne Twister engine, seeded with the value 0 to make the runs repeatable across different tests. So maybe we're emboldened by our previous findings and also look at other node-based containers, such as standard map, and think maybe we can replace this with a sorted standard vector or a sorted standard vector of standard unique pointers. Maybe that will give us similar performance improvements. So unfortunately, I don't have any performance graphs for this one. I just didn't have time to put them together. But I do have the data and I can talk about that. So in all situations, regardless of element size or number of elements, the unstable flat map, which is to say the sorted standard vector, provided better lookup performance than the other two options. And that kind of fits with what we expect because all of the data is in one location in memory. You just do a binary search on it. And standard map provides the fastest insertion. And the reason for that is because unlike with the standard list, you don't have to iterate over half of the elements on average, just the base 2 logarithm of the number of elements on average. So the search time is greatly reduced, and then the insertion time becomes what dominates. So you insert into the middle of the sorted vector or moving vector, you have to move half of the elements over on average, and that becomes very expensive. Yes?
Could you explain what the unstable flat map is one more time?
Yes. So the unstable flat map is a name I provided in that code I linked to. That is it provides a map interface, but underneath it's a sorted standard vector. The only addition it makes over the map interface is that it also provides the ability to do batch insertion by way of an iterator pair. So that way, the implementation of that was add all of the elements to the end of the vector, sort those, and then do an in-place merge and do unique. To save a little bit of performance, I did have to write my own algorithm for that because in-place merge followed by unique is a 2-pass algorithm, but you can do it in 1 pass. Benchmarking showed that the unique in-place merge algorithm gave me about I believe 15% performance improvement. And that was with an imperfect implementation of in-place merge. So what I found was that for small element sizes, unstable flat map, which is the sorted standard vector, was faster for everything, including batch insertion, other than inserting one element into the, say, 500,000 element map. It was faster to batch insert, it was faster to iterate, construct, destruct, everything. Where small here means around 100 bytes. The interesting thing that I found, though, was that stable flat map, the vector of unique pointers, was never the best choice. There was not a single key or value size that I could come up with, number of elements, anything that made that a better choice than the sorted standard vector or the map. And at first, this was pretty puzzling to me. So I had to ask myself, why does this perform so much worse at associative tasks? And I couldn't figure it out until finally I sat down and I drew a picture. And it looked something like this. So with the sorted standard vector, you go here, you fetch the memory, and then you do a compare. And then based on the results of that compare, you go to one of these locations. So unlike with the vector of unique pointers as a sequence container, you don't know where you're going to go until after you fetch the memory. So the pattern here is fetch, compare, jump. Whereas with standard map, you go here, you have the element right here, you compare. Based on the results of that compare, you jump. So you fetch the memory and you jump there at the same time. So instead of a fetch and then a conditional jump, here you just have the fetch and the compare. You don't have to have that extra step in there. Does everybody kind of understand what I'm saying there? Or have any questions?
It seems the same as the list, where you have to get to the next place before you can before you can get the next thing. So I don't know, I don't understand.
Okay.
That's different than a list.
Yeah. So with the advantage of the vector of unique pointers, when we were starting here and traversing forward, was we go here and then we send the memory request across the memory bus, go get the memory. And then while we're waiting there, while the process is just sitting idle, it can say, I know I'm going to need this next. So it sends this along. So now both of these are in the memory bus queue in the pipeline. And then it can even go here. It can start fetching more memory as it needs. So it doesn't have to wait for a round trip before it can do the next thing. With the sorted standard vector, when we're trying to do lookups, it goes to this element here, fetches this memory, and it doesn't know where it's going to go next until after it's gotten the result. So it has to wait to send the request out to memory, wait for the result back, and then it can go to the next location. So you have a round trip time to memory, and then you compare, and then you have to load another location in memory. Because when you get very large, only the local things for the sorted vector are in memory. So you might have to jump to a different cache line or a different page, or load something in from L2 to L1, or basically just go to a more expensive point in the cache. Whereas with the map, you still have to go here and wait for your comparison. You have one round trip to memory here, but that round trip includes the next data point. So you have the data here, you compare, and then you jump.
So that's what I was looking for.
Yes.
Of course, you can only jump to two places, right? So
Yes.
nothing prevents you to preload it manually.
Yes, a sufficiently intelligent compiler or the programmer theoretically could, I believe a lot of compilers support prefetch instructions, so you could make this perform a little better using compiler built-ins.
Level prefetch, right? And then I'm pretty sure this.
Yes. So that does. The point was that you could use a compiler intrinsic or inline assembly or some sort of non-portable solution like that to prefetch the memory in the case of the sorted vector to try to minimize some of these latencies. And that is correct, but as I mentioned, that requires non-standard extensions or help from your compiler. And also,
You waste that bit.
well, it's also difficult to, you have to do both fetches. And also, you don't benefit as much from future improvements in the compiler and the instruction set of your processor. Basically, any time that you have to tell the compiler exactly how to do this, you're risking that information becoming out of date and it actually becoming a pessimization instead of an optimization. Yes?
Which types were you using in the maps?
The question was, which types was I using in the maps? So the key and value types that I used for this were a class that contained a standard array. So that way I could control the size. It was guaranteed to be allocated inline. But then the comparison function always only looked at the first, it was an array of integers, so it always only looked at the very first element. So that way the cost of the comparison would remain the same regardless of key size. Does anybody else have any other questions about what I just went over with the performance of the containers? Yes.
I'm still struggling with
Okay.
unstable flat map.
Yes.
Why is the picture on the right is a regular map?
Yes, this is just regular standard map. And this is the
And that's
stable
the
flat
stable.
map.
So
Yes.
if you were to draw unstable up there, why would that be any different from stable as far as lookup?
Okay, so what the unstable flat map would look like is get rid of all of these arrows. So you go to the middle point, you have the value right here.
Oh, so it's basically encapsulating the value in there.
Yeah, it's just a sorted standard vector. It does a binary sort. So it goes here. It doesn't have to make a round trip to memory to get the value for the comparison. It just has it right there and then
Flattened
jumps.
version of the map there, basically.
Yeah, it just kind of brings those there, and those, kind of moves them all up, puts them in order.
Gotcha.
Yeah. So the question was, what would the unstable flat map, which is the sorted vector, what would that look like on this diagram? Okay. So another situation where people often use dynamic allocation is for optional values. In particular, or rather, I guess we should say, if you or your coworkers were designing a function that needs to output an optional value, what would it look like? What does it look like if it just needs to return by reference? It doesn't need to grant ownership of the thing, but just a reference to the thing. Anybody have any ideas? What would their function look like for this?
I would return a pointer.
For the by reference version, or for both? I guess I should say, you have a function. You either want to grant ownership to someone else, or just let them reference the data.
So the second one.
The second one, you just return just a regular raw pointer.
If it's, well, I guess I need to have a little more context, but if it's something, well, let me think for a second. If it has to be optional, then yes, I would return a raw pointer if I'm not taking ownership, and then if it has to be there, I would return it by const reference, I suppose. Typically, I'm not sure. I don't know if I have enough context, but.
Okay, so his answer was that he would just return a raw pointer to use the optional semantics, or maybe just by reference to const if it doesn't have to be optional. And I agree with that. That is actually would be my recommendation for how to return an optional reference to something. And if you need to grant ownership, then in general, I would say use something like the proposed standard optional. There's a reference implementation of it there, or you can use the version in Boost. The one important thing to note is that as of Boost 1.55, optional does not yet support move semantics, so that might be an important factor in weighing the performance implications of doing that. Actually, let me back up a little bit. So I kind of posed the question here, what interface is going to be easiest to use and fastest to use? Yes?
Maybe I'm missing something, but if you were going to return a pointer in the case that you're not assigning ownership, if you were passing ownership, why would you not return a unique pointer or a shared pointer? Yes, because you're not.
So the question was, in the case of returning by reference, you'd return a pointer. So why, in the case of granting ownership to someone, would you not return something like a standard unique pointer? And so that actually goes very nicely into this next part here, particularly in the question of which is faster. So if you don't need runtime polymorphism, if you're not trying to return a base class that could be any one of several derived classes, you don't need that functionality, then you have a choice to make. Do you return optional T or standard unique pointer T? And standard unique pointer T implies that when you created it, you had a dynamic allocation, which is going to be slow. And it also means that every time you use it, you have an indirect access. And that's where all of our performance issues on, in these past graphs here came from. Because of the indirect access, every time you go to something, you have to issue an instruction to fetch from memory and return. And as Chandler Carruth talked about in his keynote presentation from last year here, that also greatly inhibits what the compiler can do in terms of optimizations. Because all it sees is you have this unique pointer, which is just a class with a pointer in it. And it doesn't know, does this pointer alias anything else? Maybe this pointer actually points to something else, because the compiler doesn't have the same context that we have to know that the unique pointer is the sole owner. And even if it did, you could hand out references to that with Git, or by dereferencing it and storing a reference somewhere else. So that means that every time that you read from the value, in most cases, the compiler will have to issue an actual read instruction from memory. It cannot rely on what it has in a register, because something else somewhere may have changed it since then, other than in a few very limited situations. So when you return by unique pointer, that implies a performance overhead in most situations that you generally want to avoid. And that's why I would recommend returning an optional T for that reason.
So optional contains a reference. That's the
Optional, you can think of it as, it's basically the same as a pair of bool and the value, except that if the Boolean value is false, the value is not even default constructed. There's space for it, but there's nothing there. It also provides a slightly more convenient interface where you can say dot value if you want it to throw if it's not there. You can say get value or to return a default value if it's not there. It has a few kind of little helpful things in it that you don't necessarily get with pointers. So another issue is, rather than just returning from a function, what if you need to store this optional value? So if you use standard optional T, the one downside of this is that it is always at least as large as T. So if you have a large value, say an optional class of 200 bytes, and that represents some sort of important, let's say, some important flags for a stock or a bond or an index or something like that, and you are watching 4 million of them, and this data is only present in a small portion of them. If you use optional to represent that, you're always paying for that space, even though maybe only 1% of them have it. Whereas if you use unique pointer T, it's always size of T, 64-bit platforms is going to be 8 bytes. So rather than paying 4 billion times the size of the object, you're only paying 4 billion times 8. So you can have very important space optimizations by using unique pointer there to represent a value that you might not have. In general, though, you will get better performance out of optional. It's only when you have a whole lot of them and you expect them to not be there that you should really consider using unique pointer for optional values. So yeah, one thing I wanted to mention is don't be afraid of returning by value or passing by value or anything like that, because in many situations the compiler will elide copies, and it is getting better at doing that all the time. So if you just have some function, you declare a variable at the top, you do some stuff, and then you return that variable, the compiler will not copy that. It'll be constructed directly in place. All compilers do this. GCC, Clang, Visual Studio, Intel. There will be no copy there. You don't have to be afraid of returning by value. You don't have to return a unique pointer to minimize the cost of that. That's referred to as the return value optimization in that case. And also, most moves are cheap. If you're returning a standard string, there is no reason to return a unique pointer to try and make moves cheaper, because string is already cheap to move. Same with vector, list, all of the containers other than array. So if you want to return a dynamically allocated value, this whole talk I've been talking about unique pointer and kind of ignoring shared pointer. So I want to kind of correct that now and talk a little bit about what it does mean to return a unique pointer and a shared pointer. The advice that you generally see is prefer U instead of S. Prefer this function definition where you return a unique pointer rather than this function definition if you're creating the object. Does anybody have any idea why this is generally the advice? Yes.
Unique pointers are convertible to shared pointers, but not the reverse.
So the answer was that unique pointers are convertible to shared pointers and not the reverse. And the reason for that is because unique pointer has a release member function, because it knows it is the only one who owns this object. And actually, I believe shared pointer is move constructible from a unique pointer.
Yes.
Yeah, so you can actually just move the unique pointer into the shared pointer because it's the only one who owns it. You can't go the other way around. You can't transfer the ownership from the shared pointer to the unique pointer, because the whole reason that you're using shared pointer is that other people may also be sharing ownership with you, and you have no way to take the ownership from them.
You could add that the cost of constructing a shared pointer is substantially higher than constructing a unique pointer.
Yes, so the point was that the cost of constructing a shared pointer is substantially higher than constructing a unique pointer, because it also has to allocate space for the control block that contains a reference count to the number of shared pointers and a reference count for the number of unique pointers. Yes?
If you're using make shared and make unique, that's unlikely to be the case.
So the point was that if you're using make shared and make unique, that is unlikely to be the case. So it is true that using make shared will not allocate the control block separately, but it does still have to allocate that space.
Correct.
And if your class is, say, 60 bytes, and you allocate it with a unique pointer, you have a 60-byte memory allocation, probably rounded up to 64. Whereas with make shared, now you probably have something like a, 72 or 70 or 80 byte memory allocation. Whereas in processors, the cache line is typically 64 bytes. So now your total allocation is going to be larger than a cache line, and that can be a pretty significant performance penalty. So that also, though, is an interesting point about how to return from a function. And that is the importance of, well, I guess I should say, yeah, the importance of make shared, we just went over that. It allocates the control block with the object, one memory allocation instead of two. But there is a difference between libraries and applications, where a library may say, I want to be flexible. I don't know what my users are going to want with this. Maybe they want a unique pointer, maybe they want a shared pointer. So I'm going to do the flexible thing and return a unique pointer. However, an application developer has the advantage of knowing, in many cases, how it's going to be used. And if you expect your object to be used with a shared pointer, but you define an interface that returns a unique pointer to be flexible, it's the same as not using make shared, because now the object is allocated in one location and the control block is allocated somewhere else. So, yeah, if you expect that the object will be used in a shared pointer, you should return a shared pointer from your function. You could possibly have two overloads of the function so they could decide, but that requires duplicating a lot of your logic in some cases. So I want to talk a little bit about value semantics. I won't spend too much time on this because we've had a lot of other discussion at this talk. Primarily, though, in regard to shared pointer. Shared pointer is last on that hierarchy. Performance alone would put it there. It is definitely the slowest of the three ways to own memory because of that reference count. However, indirection is powerful, but with that power, it can be very difficult to understand shared pointer code. Because the implication is I have a shared pointer, I do something with it, and I expect it to be in a certain state. But because I'm using a shared pointer, that's saying someone else probably has that too, and maybe they changed it. So now, even if I just changed something in my code, I can't expect that it's still that same way. I can't rely on value semantics. I can't rely on the code that I'm looking at being the only code that's changing the object. So when possible, if you do need a shared pointer, try to make the object const, because then you don't have the issue of someone somewhere else changing it. There's no one who can change it, at least through this shared pointer. Yes?
This only actually works if you basically run the equivalent of make shared const, because you can only guarantee, if you get a shared pointer const like returned from a function, the other side of that function could still have a non-const shared pointer to that element?
So the point was that the only way that you really get a guarantee out of this is if you initially create it with, say, standard make shared t const, because then you know that the object itself was initially created as const. Essentially, the issue is that even though your reference to the object, you can have a read-only view, the object itself might be modifiable. And while I do agree with you in principle, on the other side of that, if you're only giving out shared pointers to const, if you're the one with the mutable shared pointer, then you at least know in your code, I can change stuff. They can't rely on it, but I can rely on them not changing it. It's basically, the idea is limit the amount of places that can mutate it. You get the same problem with t pointer instead of t const pointer. Scope-bound resource management is very important in C++. Basically, you acquire a resource, usually in the destructor, or in the constructor rather, and then you release it in the destructor. So your lifetime is within this particular scope. And if you write structured code, that automatically creates nested lifetimes. We use functions, not goto everywhere, because it makes code a lot easier to understand. You start here, you go through it, and then you're done with this code. You don't have anything jumping into the middle. So shared pointer, in many ways, unstructures structured code. The reason for that is because code somewhere else could be making modifications in the middle of your code, so to speak. And a lot of people seem to use standard shared pointer as kind of a way to avoid structuring their code. They just kind of, oh yeah, we're having memory leaks, I'm going to throw a shared pointer at it and hope they go away. You will fix the memory leaks, but instead of having one problem, now you have two, kind of thing. You make the code harder to read, you make it less performant. There's a whole host of issues associated with using shared pointer when you don't need to. I would say at least 90% of the code I see that uses shared pointer should not have used shared pointer. Should have used unique pointer, or more likely, just a value. I'd actually say that shared pointer is probably the second most overused class in the standard library after standard list. The one situation where I do recommend shared pointer is in multi-threaded code. That is the reason for its existence. So for instance, the reason for this is that you could be modeling something that must hold on to data, but the duration is dependent on runtime factors. So a concrete example for this would be maybe you are listening to a data stream. You bring in the data, you normalize it in some way, and then you send it back out. So you have one input and you have an unknown number of consumers. So as the data comes in, maybe you have 5 consumers that have all registered interest and they want to listen to it. And you want reliable delivery, so you're using a TCP socket for each of them. So you bring in the data, you normalize it. How I have used this in the past is I store the data as a shared pointer to the data. And then in each of the queues for the 5 consumers, we put the shared pointer in. Because you don't know how long it's going to take each consumer to get through each message. You wait until each of the 5 consumers has consumed their message and then the data is gone. Yes?
Of course, that's not one issue for multi-threading. If you have a single-threaded but event-driven application, then you pretty much have the same scenario. You might only have one thread, but the lifetime of the objects still depend on the events that come in, right?
So the point was that you don't necessarily get this situation in multi-threaded code. You could have a single-threaded, event-driven application where the same sort of pattern comes up. I would say in that situation, even if your application is single-threaded, you are trying to give it the appearance of multi-threaded code, and in that case, that's the model that that's what you're trying to model. And at some point in the future, you may make it multi-threaded. And so at that point, it may read easier because you're trying to basically act as though there are multiple things happening at once.
But there still are. It's just that they're time sliced. But you absolutely need a shared pointer-like thing in such a system, because for exactly the same reason. However, you might want to have a different shared pointer that doesn't do locking.
So the point was that you are still responding to events that come in at unknown times, but you're on a single thread that maybe time sliced, it's context switching around. And so in that situation, though, you may not want to use standard shared pointer itself, but maybe something that provides similar functionality without the atomic reference count, just a plain reference count. And I would absolutely agree with that. That would be a situation where I would expect to see a fairly significant performance improvement from writing something like shared pointer, but not using shared pointer itself. So I think one of the most misunderstood things since C++11 is raw pointers. A lot of my coworkers come to me and they think that shared pointers are here, so we shouldn't use raw pointers anymore. And I would disagree with that. I say that smart pointers do not deprecate raw pointers. The important thing is that raw pointers don't own memory. It is absolutely fine for them to reference something. They don't own anything. They're just a reference to it. You can think of a pointer as an optional reference. So a reference always references one thing and it always references the same thing. A pointer, you can change what it references. It might reference nothing, but as long as that's what you're using it for, there's no problem with pointers. A lot of people a lot of times we as kind of the community give the advice of, oh yeah, don't use raw pointers. But what we really mean is don't use owning raw pointers. We kind of get all excited. Yeah, smart pointers, that's the way to go. No more resource leaks. You get the same thing by using raw pointers just for references. Does anybody have any questions about anything we've covered at this point? Yes?
Take on using a boost optional T-reference or something like this?
So the question was about something like boost optional T-reference. So the discussion for standard optional covered this. And it was originally proposed to follow the model as defined in Boost of having a specialization in optional for T-reference. And it would be implemented internally as a pointer. So that way it did not have to store the extra space for the Boolean. Ultimately, the reason that it was rejected, as far as I can tell, at least one of the main reasons, was that it would lead to unexpected behavior. If you have a reference to const and you bind a temporary to it, the lifetime of that temporary is extended to be the lifetime of the reference. Whereas an optional reference to const does not have that semantics. You'd be binding it to a pointer to const, it would initially die and you'd have a dangling pointer. I think that is pretty good advice. Like that is something that I think would trip up a lot of people who, they learn that rule. They're used to being able to say tconst ref and it's safe to store stuff, but then they use optional and suddenly it isn't. So I think that using pointers here instead of optional is will lead to fewer surprises. One issue though is that with legacy interfaces, people might get confused about whether this pointer owns the memory or it doesn't. So there are a few ways that you can solve this. In Marshall's talk earlier, the idea was brought up to use something like a view pointer or a raw pointer or some sort of template class that is the same thing, maybe even just a type def for it, just so you can document it in the interfaces. In my experience, I find it more helpful to just go through module by module. And I take this whole library, I clean it up, and then I solve the human problem of training people, we're moving to this, raw pointers don't own memory anymore, this is where we're at, and just kind of sweep through it because it doesn't really take that much time to convert between owning raw pointers and non-owning raw pointers. Now, and personally, I believe that to be the best solution for that. Yes?
One thing to remember is if you return an optional by value, don't dereference it before you assign it to something.
Uh,
Don't dereference the value and then assign that to a reference.
So the point was that if you return an optional by value, don't dereference it before you assign it to something. Could you explain why?
If you return an optional of standard string, for example,
Mm-hmm.
and you assign that to a const reference to a string, after dereferencing the optional is a temporary, and its lifetime will end.
Okay, so the point.
It's not.
Okay.
It's not being assigned to reference.
Okay, so the point was that you, if you return an optional by value from a function, and you try to bind the value that it contains to a reference to const, that does not extend the lifetime of your temporary, and that is an important thing to keep in mind. You can't just replace all of your code everywhere with, oh, okay, return optional, and then just say dot value, and exceptions will take care of everything. Because if you have code that relies on the reference to const lifetime extension behavior, then you get a dangling reference. Although, maybe the real problem there is just that binding a temporary to a reference to const is pretty confusing. A lot of people aren't familiar with it. Maybe that's something you shouldn't be doing all that much.
I was gonna ask, no, there you go.
If the type that's involved in all of that is cheaply movable, you can just avoid the whole problem by moving it into an actual object as opposed to a reference. And then you don't have to worry about the temporary disappearing. You want it to disappear.
So the point was that if the type is cheaply movable, you don't have to worry about binding it to a reference. I would actually say even if the type is not cheaply movable, you don't have to worry about that. Because with the return value optimization, essentially what the compiler does is it passes in a hidden reference parameter that it knows doesn't alias anything. So it avoids all of the aliasing penalties to performance. And it just, anytime that you talk about it, it just references, it constructs it right at the location referenced by that memory. So there's never any copy, never any move, anything like that. It's just right there. So you actually don't even have to worry about whether it's cheaply movable or not in most situations. Now, there are a few situations where the compiler cannot perform return value optimization. This varies depending on compiler, and they're becoming less and less regular as time goes on. I know that in Visual Studio, at least 2012 and earlier, you have to always be returning the same value. You can't say, if some condition, return this value, else return this other value, and have return value optimization kick in. The other situation would be if you're returning a function parameter, then there can't be a return value optimization there because the lifetime started before the function. However, the trick of binding it to a reference to const still does not save you because it's moved into the return value, and then that return value is moved into your local variable, but in practice, compilers eliminate that second move. So regardless of whether you store it in a value or a reference to const, you still have one move. You haven't saved anything.
This idea of returning a value and binding it to a const or whatever, do people really do that? I mean, is that a common thing to do? Because I just wouldn't, I understand how it works completely, it just wouldn't really come up that much with me.
So the question was, is it a common thing for people to try to bind a temporary to a reference to const to extend its lifetime? And I would say no, it is not common. Sometimes it can come up, for instance, in generic code where it's safe to bind anything to a reference to const. You don't have to worry if this function returns by value or reference. I have seen a few people do it just, in a regular function, so they don't have to check and see, did this return by value, did it return by reference to const, or maybe it's changed. It's always safe to do that as long as you're just taking the exact function call and not doing anything with it. But yeah, I haven't, it's not a very common thing to do, just something that is out there. Okay. One other somewhat overlooked example, or rather overlooked in its importance in some situations, is the compilation firewall, also known as the pimple idiom or the handle body. Basically, the idea is, let's say you have this class, and it has a whole bunch of things in it, and each of these things has their own header. So it takes a very long time to compile code that includes this header. So you have this, it takes a long time to compile. What you can do instead is change it to this. You forward declare an implementation class. The only data member that you have is a unique pointer to the data member that you forward declared, and you have all of your interface in here. So what this gives you is that when you change the implementation of your class, nobody knows about it. Nobody has to recompile. It's very quick to compile this because there's very few, if any, headers. And it also is important for, so I mentioned minimize compile times, minimize recompilation, but it also gives you a stable ABI. So the layout of this class is always going to be a single pointer. That's it. Doesn't matter if you store a string inside your implementation, a vector, 19 ints, nobody has to know, nobody cares. And if used with care, this can work around binary compatibility problems in third-party libraries. This situation actually came up at my work recently. A data vendor provided us a third-party binary library to use to decode their stream of data. But they use Boost in their library, and we use Boost in our code. They used Boost 1.51, and we were using Boost 1.53. So they did do one thing, though, that was very helpful. Boost has an option where you can define something when you build Boost to change the namespace name. So they changed it from Boost with a lowercase b to Boost with a capital B. And everywhere that they used it, they used Boost with a capital B. And the reason that this was important was it means that at the link step, they can link against their version of Boost, we can link against our version of Boost, and they're completely different symbols, the linker doesn't care. However, the issue is that their headers did include Boost. They exposed Boost in their headers. They had functions that return Boost stuff, Boost data types. And so we couldn't include any of their headers at the same time that we included our headers that also use Boost, because they just say, include Boost / whatever. So the effect that would have is, we have our Boost in the include path when we include their headers, and it includes our Boost 1.53 with Boost with a lowercase b, and they're referencing Boost with a capital B. So now we get a compile time error. So the solution for this was to use a class that looked a lot like this. And we had to take care, separate it into its own library that we would compile. And in this other library, its headers did not expose any third-party library code, did not expose any Boost code, did not expose any of our own headers. All it did was provide the minimal interface, just using standard C++ headers at most, like standard vector, int, stuff like that. And the implementation translated all of their functions to our own functions. So like instead of returning Boost uint16t, we could return standard uint16t or short or int or whatever we wanted, as long as it wasn't Boost. And then we compile this separately as its own library file. And then our application code then links against and includes the firewall library here that separated us from the third-party code. And there was no include problems because we never had to include their Boost, we just had to link against it. We were able to safely include our own headers here because there was no overlap. So yeah, there was no other way other than rewriting all of our own libraries to not use Boost, which would have been a pretty massive undertaking. So in summary, you should use a smart pointer only for dynamic polymorphism when you cannot achieve this without dynamic allocation, so returning from function or storing the data. Minimizing compilation dependencies, Pimple, what I just talked about. Optional values that could be very large and you expect them to not be there very often. You can save a lot of space that way. You can enable moves on non-movable types. You can optimize moves on slow to move types. And in all other cases, I would say use an automatic variable. And then as a side note from what we learned here through the cost of access to memory, prefer cache-friendly data structures. Prefer vector and DEC over list. Prefer a sorted vector to map when you can. I often find that if I have an algorithm where it would perform better with a data structure that isn't vector, I should rewrite my algorithm to be good with vector rather than changing my data structure to not be vector, because the performance wins are just that big. As an example of that, actually, I had a situation where I had a whole bunch of things, and I was basically trying to apply a filter operation on it. Repeatedly apply filter. I could remove maybe 80% of it, or 90% of my data, and maybe I had 1 million of these on each run. And so my goal was to keep applying this operation as new data came in until I found what the real result was, because all of them represented possibilities. So my initial implementation from way back before I knew about locality of reference and caches and everything, I just had a vector, and I went along, and when I applied my filter, I just removed the element. So that caused everything to shift with each remove. So if I was removing 80% of it, I'd go through 2 elements in, remove it, shift over 1 million. 3 elements in, shift over 1 million, and keep going through, really slow. So then I read a little bit about data structures, and I thought, oh, list, yeah, that's really good. You can delete in constant time. So I went through, deleted it, now it's just a relink. It gave me really big performance improvements, but it was still too slow. So I read a little bit more, and I found the algorithm header. And then, rather than actually deleting each element, I called standard remove if. So that, rather than actually deleting the element there, it does move assignment, or at the time, since this was C++ 2003, a swap. It swaps the elements in place in a way that minimizes the number of swaps. And then at the very end, you call erase to delete all of the extra junk elements that were moved to the end. And this gave me just as much of a performance improvement as switching from the original vector implementation to list did. And then it was fast enough. So that's what I mean when I say pick a different algorithm if you can't use vector, at least whenever you can. It is a huge win. Rather than using standard map, consider if you can use a standard vector that's sorted and insert in batch. If you can insert, say, 1,000 elements at a time, then that can give you a big performance improvement, because now lookups are very fast. And that is my presentation. Does anybody else have any questions?
I was going to make a comment.
Yes.
The discussion you had about the difference in speed between the stable flat map and the map, you could have helped that somewhat by creating a custom wrapper that was actually the object in the vector that had a copy of the key, so that you didn't have to indirect out to the real object to do key comparisons. Much like what the map does inside, where you've got a node that actually has the key in it, which gets you some benefits back of not having to indirect all over the place just to do your binary searches, but they're all smashed together in an array.
So the point, and correct me if I'm wrong, was that rather than with the stable flat map using a unique pointer to a pair of key and value, I could have used a pair of key and unique pointer to value. Yes, that is an interesting optimization, and I will look into that.
That would only work for small.
Yes, if your key gets very large,
What is
then...
the number of elements?
I'm sorry?
What is the number of elements?
Yeah, you'd get the same sort of... It would bring the performance more in line with vector, but make insertions a little bit cheaper. So as the elements grew very large, insertions are more expensive in that case, but it might at least make the data structure usable. Yeah, that's a good point. Yes?
This is not a question, but probably a funny story of VQ, well, probably Q. I guess one of my previous companies, we had an XML parser. So one of my previous company, we had an XML parser. It was a DOM parser, and it used vectors to represent tags and in basically a tree structure. And at some point, someone said, why do we use vectors? We actually inserting data
to each element, and then really thought, why not a queue, right? It sounds completely plausible. Now what happened is that the memory footprint of our library from, I don't know, for a big XML from 700 megabyte went up to 7 gigabyte. And apparently the reason for that is that DQ pre-allocates 512 byte block of memory by default, even when you just default allocate it. Now that was pre-C++ 11. I'm not sure if this is still in effect, but that basically killed us to use DQ, because in an XML parsing, most of the end nodes are empty. Right.
So one other thing that I guess is kind of the opposite of that is that the Visual Studio implementation of DEC takes the opposite approach, and the block size is always 16 bytes, whereas on other implementations the block size can be a little bit larger. The effect is that on Visual Studio, DEC is very close, and for large element sizes it's the exact same, but with some overhead of using a vector of unique pointers. There is, I guess, one other thing I guess I should mention then with regards to standard DEC or DQ. I guess I don't know how it's supposed to be pronounced. But it is the default data structure for the container adapter stack. And I believe that that is actually probably the correct decision. So the reason for that is with a stack, you add elements on, and then you're accessing the most recently added elements. So the only thing that you really care about being, the only part of the data structure where you care about the locality of reference is that very top few elements, and those are all going to be allocated together with a DEC, as long as you don't have a 16-byte block and your objects are 16 bytes. So in some situations, DEC can, you can avoid the performance penalty of vector reallocation moving everything and still get all of the locality of reference benefits. I believe I saw a question, comment over here. No, okay. Anybody else have anything else to say? Yes?
One more. We really didn't talk about the cost of constructing these different things. If we're talking about iterating or lookups, but if you're just using it a little bit here and there, and the main cost is construction, how would you expect that to play out?
So the point was that most of this discussion was about access to memory, and I did not spend that much time on allocation. I did have a few more slides that actually did go over that. They got deleted somehow, but I'll just explain what the results were. So as bad as the cost of accessing memory through a pointer is compared to accessing memory not through a pointer, the cost of allocating memory from the heap is much worse than the cost of allocating on the stack. Stack allocation is just increment the stack pointer, whereas a heap allocation involves, system call, get some memory, it has to order things, and then after you're done with it, you have the issue of memory fragmentation, so it has to recompact things. There's all of this extra machinery involved with heap allocation compared to stack allocation. So if you go to, let's see. So if you go to this link, you can pull down the code, and you can actually see the effects of this on your own system. It includes performance tests. If you run especially the map test suite, it times the cost of constructing the map with each of the three types of map, accessing the memory, inserting, and the time for destruction. And when you look at that, the cost of standard map over standard vector for allocation is pretty significant. So for instance, on a particular test, it might be 1 second to allocate some number of elements in a vector, and standard map might be 1.8 seconds. And then on the other end, for destruction, it's even worse, because with standard vector, it might be 5 milliseconds, whereas with standard map, it might be 800 milliseconds. That is actually the larger source, because with a standard map, it has to, again, follow each of those pointers and deallocate each node separately. Standard vector just says, here you go, you have the memory again, I'm done with it. And the other effect that has is that when you use standard vector, because all of your memory is contiguous, you are creating less heap fragmentation for the rest of your system. Whereas with standard map, you have all of these individual chunks that need to be managed separately. So you have more overhead in your system allocator, and when you're trying to allocate other memory, you might have a piece here, and a piece here. And even though you have enough memory in your system available for a 1 gigabyte chunk, it's not contiguous, so you can't actually allocate another vector.
One thing.
Yes.
For node-based containers, we implement them. We overlay the standard containers because we want to have allocators.
Mm-hmm.
And even with allocators, having adaptive pools for node-based containers is such an enormously huge win that once you have that, it doesn't even matter if you have a stack allocator, you can't get more than about 3% more out of it. But without the pools inside the node-based containers, it's just really bad without an allocator. So I would suggest that if you want to have all the advantages of everything, put pools in your node-based containers and then use a stack allocator for everything else, and you'll get exactly what you said here.
Mm-hmm.
And it's true, construction is, destruction is a dominant cost. So this would actually make that better, I think,
Mm-hmm.
because there would be larger chunks for the node-based containers that they could get back.
So the point was that node-based allocators can help a lot with these costs, or rather pool-based allocators, sorry, where...
Hold on, I think what we mean is pools, adaptive pools inside the container.
Okay.
So in other words, there's no virtual function, there's no anything, it's just there and it's all good. The allocators, the way we think of them, the polymorphic ones, that you take the address of a polymorphic resource at construction, and there is a virtual function cost for allocating memory. But the node-based containers win big because they don't have that cost, and the nodes are the right size, and it just all happens inside the container.
Okay. Could you explain a bit what you mean by...
Sure.
I'm sorry. Yeah.
I'll give it a shot.
Yeah.
Okay, so just...
I don't have to...
Sure, no problem. I understand. So what I was saying was, it turns out we've determined experimentally that for our node-based container types, it's far superior, rather than going to some general purpose allocator or even one supplied, that we have adaptive pools built into the container. And that makes an enormous difference, and we don't even need really any special allocator. The second thing is we have something called a buffered sequential allocator that allocates memory right off the program stack, and that's used all over Bloomberg, and it's just like, the best thing. So anyway, I just wanted to say that. Okay.
Yeah, and so I guess now would also be a good time to bring up, there is a fairly good, but at this point probably somewhat dated article that compared the performance of different allocators. If you just search for allocator performance in C++, it'd probably be one of the top results. They looked at custom allocators written by different, I believe they looked at top open source applications that had written their own allocators. And they found that on older compilers, the custom allocators often were superior to whatever came with the system. But as you upgrade the compiler, that difference shrinks and eventually becomes negative, because the compiler vendors are always moving forward with the allocation strategy. Whereas, they were using allocation strategies that were good for their time, but, generally you write the allocator, you get your performance, and you say, okay, good, now let me move on somewhere else. And then 10 years go by, you have performance, you think, we already have our fast allocator, we don't have to look there, let's look somewhere else. So unless you're someone like Bloomberg who can afford to.
Sorry, maybe allocators, the paper that I know the paper you're talking about, you can't do better for a general purpose allocator than the one that's on the system, unless it's an arena allocator,
Yes.
and you know what's going on, and particularly you can avoid the synchronization because you're doing on the program stack. You don't need to have a lock, and there's no question that it's faster, but it's not because I'm better at writing allocators. It's the nature of the
The special purpose allocator can outperform a general purpose allocator
Exactly.
as long as it's tuned to your special purpose properly.
Exactly. Now, I want to be very clear.
Yes.
I wouldn't try to write a general purpose allocator. There's no point.
Yeah, I guess the point I was more trying to make was that unless you are a large company where you have the resources to keep up with your special purpose allocator, at some point the general purpose allocator might outtake what used to be better.
Okay.
Yes.
Have you tested the performance of a B-tree compared to the standard map as it solves a few of the previously mentioned problems?
The question was whether I tested the performance of a B tree as opposed to a standard map, which is usually implemented with a red-black tree, and in GCC it is. The answer to that is no, I have not. I also have not tested out the performance of skipped lists, which could also be used as an implementation, but yeah, I just haven't had time to test out the different ways of doing that. Yes.
You talked about never use a standard list, right?
Yes.
So do you think that should be deprecated from the standard?
So the question was whether I believe that standard lists should be deprecated and maybe even someday removed from the standard. And I believe the answer to that question is yes. If you read Design and Evolution of C++, I believe is where Bjarne Stroustrup explains why he supported adding standard lists to the standard. And it was basically just because if he didn't, everyone would ask where it was and implement it themselves. And he didn't want that. I believe that a linked list data structure can be good, but I believe as specified in the standard list is not the appropriate data structure. One advantage that it can give you that I haven't talked about here is with list splicing. You can splice, the middle of some list into the middle of another list in constant time, and no other data structure can give you that. But the problem is, because size is guaranteed to be constant time, and because standard list has a size member function, standard list has to provide constant time size. And it cannot do that in the general case with splice. If you splice an entire list into your standard list, it can, because it has the other size. So I would say I would support deprecating standard list, maybe replace it with like double list or forward back. I don't know what the standard name would be to complement standard forward list, but I would not provide a size member function, because then the one thing that lists are good for, splicing, would become fast as they should be. Yes?
I believe that you can implement the standard requirements in a way that results in splice having constant time and effectively caching size.
So the point that he brought up was that he believes that you can implement splice with standard list and still following all the requirements through caching the size. That may be true in some cases, but you cannot, in the general case, have a pair of bidirectional or forward iterators and pass that into splice and get constant time with the requirement of having constant time size. The only way you could do that, you'd have to walk through it, find the size of the range, and then add that to your size. So in some special cases, you might be able to get that.
Is you calculate the size when someone calls size as opposed to when you perform the slice.
But you can't, because the standard requires that to be a constant time operation.
Yeah, the standard was changed in C++ 11 from recommending constant time but allowing linear time to requiring constant time for all containers that provide size. If you don't provide a constant time size, you're not a standard container.
Well, it would be amortized constant time if it was cached.
It requires constant time size, not amortized constant time size. So if nobody else has any questions, I'll call that good. Thank you.